Carl Schwarzschild and Alexander Friedmann used Einstein's field equations to construct the first exact mathematical maps of the cosmos. Their solutions worked, but they harbored a severe mathematical defect: points of infinite density where the laws of physics simply ceased to function. In the 1950s, the physics community largely dismissed these singularities. The exact solutions relied on assumptions of absolute homogeneity and perfect spherical symmetry, idealized conditions that do not exist in the actual, messy universe. Einstein himself rejected the idea that these infinitely dense points were real physical predictions. He argued they were merely mathematical glitches, artifacts born from demanding perfect symmetry in the equations. Early cosmologists assumed that in a realistic universe, full of irregular shapes and chaotic trajectories, collapsing matter would simply swirl past itself. Particles would miss each other in the center, avoiding any central point of infinite collapse. To settle the debate, physicists needed a way to strip away the assumptions of perfect symmetry. They needed a mathematical tool capable of determining if gravity inherently forces a singularity, regardless of how chaotic the starting conditions might be. In 1955, Amal Kumar Raychaudhuri provided that tool. He bypassed specific models of gravity entirely, choosing instead to study the pure geometry of how continuous fluids flow through space and time. A flow is a continuous bundle of time-like world lines, representing matter moving forward in proper time. A four-velocity vector field dictates each particle's direction. A projection tensor isolates an orthogonal cross-section. Tracking its deformation reveals if the area shrinks to zero, indicating collapse. To understand the ultimate fate of gravitational collapse, we must first decode the pure kinematics governing this cross-sectional geometry. When we take the covariant derivative of the velocity field, the mathematics naturally splits the evolution of the flow into three distinct geometric transformations. The first is expansion, denoted by the scalar theta. This is the trace component of the derivative, representing the isotropic rate of change in the cross-sectional area. It measures whether the bundle uniformly scales up and scales down without altering its base shape. The second is shear, or sigma. This is the symmetric traceless part of the derivative. It represents volume-preserving distortion. The bundle might stretch in one direction and compress in another, changing shape while containing the exact same amount of space. The third is rotation, or vorticity, denoted by omega. As the anti-symmetric part, this describes the pure twisting of the worldline bundle around its own central axis. These three components lock together to form the Kodazzi-Raychaudhuri identity. This equation tracks the rate of change of expansion over time, dictated by the squares of the expansion, shear, and rotation terms. Because shear is squared, its numerical contribution is strictly positive. In the equation, it subtracts from the expansion, actively pulling the world lines together. Rotation, however, carries a negative sign. It acts as a centrifugal force, resisting convergence and pushing the lines apart. At this stage, gravity has not entered the equation. Pure geometry alone dictates that shear forces matter to converge, while rotation forces it to diverge. To turn this abstract geometric identity into a functional law of gravity, we must apply the Einstein field equations to the underlying curvature. The identity contains a term for the Ricci curvature tensor, which describes how the underlying spacetime bends. By applying Einstein's equations, we substitute this geometric curvature term directly with the stress-energy tensor, which describes the actual matter and energy present in the fluid. This substitution yields a new physical term, the active gravitational mass density. It is defined as the energy density plus 3 times the pressure divided by the speed of light squared. In standard Newtonian gravity, mass density alone determines gravitational attraction. But in general relativity, we see the explicit addition of the pressure term contributing directly to the active gravitational mass. This creates a direct contradiction with classical mechanics. In classical physics, internal pressure pushes outward, resisting collapse. But in general relativity, an increase in internal pressure, or energy density, amplifies the active gravitational mass of the fluid, intensifying the inward gravitational attraction. Under general relativity, a dying star cannot rely on extreme internal pressure to halt its collapse. The intense pressure becomes the weight that crushes it. By treating the Raychaudhuri equation as a Riccati equation, mathematicians transform the expansion parameter into a second-order linear differential equation. This allows us to track the acceleration of a single scale factor for the volume across proper time. If the matter obeys the strong energy condition, its energy density plus pressure remains positive, then the active gravitational mass is positive. For normal matter, gravity remains strictly attractive. To guarantee that this attractive force causes the world lines to converge, two specific environmental conditions must be met. The fluid must be irrotational, meaning it lacks vorticity to push the lines apart, and the cosmological constant must be zero or negative. When these conditions are satisfied, the mathematics yields a definitive result. The second derivative of the scale factor is strictly negative. The curve representing the volume of the fluid is relentlessly concave downward. The mathematics universally mandates geodesic focusing. Matter will inevitably be drawn together, regardless of whether the universe began with perfect symmetry or absolute chaos. This graph plots the scale factor against proper time. The universe is expanding, but gravity forces the curve to bend downward. Tracing it backward, the downward concavity dictates it must crash into the horizontal axis at a finite time. The scale factor reaches exactly zero. At this 0 point, the world lines of all matter converge. The energy density, pressure, and spacetime curvature escalate indefinitely, resulting in a spacetime singularity. This is the mathematical proof of a hot Big Bang. In the 1960s, Stephen Hawking recognized the implications of this focusing theorem, applying it to the global structure of the universe to confirm that a cosmological singularity was inescapable under classical conditions. Roger Penrose utilized these same geodesic focusing concepts, combining them with the geometry of trapped surfaces. He proved that once a star collapses past a certain threshold, the formation of a black hole singularity is inevitable. Hawking and Penrose used Raychaudhuri's engine to definitively prove that singularities are not mathematical errors, but unavoidable features of classical general relativity. The focusing theorem also maps out exactly what is required to avoid a singularity. A universe model needs massive rotational vorticity, an overwhelmingly large positive cosmological constant, or a complete violation of the energy conditions by exotic matter. Because normal matter always obeys the energy conditions, any such violation points directly to the extreme environment of the very early universe, where the classical laws of general relativity break down and quantum effects take over. Because Raychaudhuri's equation is an identity of pure geometry, it adapts seamlessly to alternative theories of gravity. It functions perfectly in non-Riemannian models, such as Einstein-Cartan theory, which introduces the effects of spacetime torsion. Today, physicists apply the null geodesic version of the equation to modern string theory and the holographic principle. It acts as a probe in ADS-CFT correspondence, tracking the flow of degrees of freedom from a lower dimensional boundary deep into the bulk of a higher dimensional space. Raychaudhuri's work provides a rigorous geometric description for the convergence of world lines. This framework allows physicists to scale from the classical collapse of a star to the quantum behavior of holographic systems, tracking how matter and information flow through the most extreme environments in the universe.